Greetings, ladies and gents. Today I'm going to go through my little homemade pH meter. I put together this one for doing soil testing around the house and maybe checking some liquids, but primarily trying to make things grow a little better. Well, if you're watching this video, it's a pretty good chance that things aren't growing quite right. So before we even get into pH, you need to go ahead and see if you can run one of these soil tests. If you're in or near a large city, you probably have an agricultural extension service from the technical college that's in your state. You definitely want to drop by and pay them a visit and take a soil sample to them. The instructions should come with the sheet, and you should be able to find this on the internet with your particular university. There should be a representative once you get your test back that should be able to tell you what all this means, but you want to pay particular attention to make sure that nothing is deficient and probably nothing is exceeding what should be the total amount your plants are going to need. Once you have this information, you should know exactly what type of fertilizer you need to use and if you need to add anything to the soil beyond fertilizer. As you can see here, the cost is pretty minimal. In a whole lot of states, it'll probably be done for next to nothing or for free if you have a large agricultural area in your basic vicinity. Before I get into the actual device and how to use it, for those that don't know what pH even stands for, I'm going to go through a little bit of preliminary background information just to introduce the concept and make sure I've got a good fundamental basis for discussing the actual device itself. For those of you that are already pretty well up on the pH concept and just want to skip ahead, here's a little index on where you can go in the video if you just want to go to the actual device and how to use it. Okay, so what is pH anyway? pH is actually a measure of how acid or basic the soil is. And for purposes of this video, I'm going to use the term basic and alkaline interchangeably. More fundamentally, it can be thought as the amount of free hydrogen available. pH is measured on a logarithmic scale from 0 to 14, with 7 being neutral, below 7 being acidic, and above 7 being alkaline or basic. pH is always written with a small p and a big H. Now, as to exactly what pH stands for, the best definition I've come to agree with is the potential for hydrogen. As far as I know, there's no exact definition of what pH actually stands for. Well, I'm sure somebody said, okay, so that's great, nice technical stuff, but why should I care? Why does it matter to me what exactly pH is in my soil at home? Well, to put it simply, pH has to match the plant. If the soil is too basic or too acidic, then the plant either won't grow at all or won't grow very well. Just for reference purposes, here are several common substances and their pH values. Note that distilled water and rainwater have a pH of around 7, where salt water and tap water have a pH of around 8. That pH of 8 for tap water will be important a little bit later on in the video. Let's take a quick look at the common plants in my area and their pH values for best growth. First on the list is azaleas. In this case, most azaleas like a 5.0 to 5.5 pH. Next on my list are hydrangeas. The flower color can actually be adjusted by varying the soil pH. In this case, if you make it more acid, the flowers are more blue. If you make it more basic, the flowers tend to be more pink. I've also got several sago palms on the property. As you can see here, 6.5 to 7.0 for a pH. And lastly, 3 of the more common grasses in the area. Most of the lawns around here are composed of St. Augustine and Bermuda. There's definitely some bahia floating around. As you can see, bahia grows just about everywhere. Right about now you can see why I wanted to go ahead and make my own pH meter. Obviously I could gather multiple samples and go down to the agricultural office and have them run each sample and give me multiple reports, but that would mean multiple trips to the ag office and also a pretty good expense, which basically is going to be more than this pH meter is going to cost me. To add to my testing needs, the pH level also varies with soil depth. It may be pretty close to correct on the top and deficient, meaning too acidic, as you go deeper. Generally, when they tell you to take a pH sample, they tell you to go dig a little deeper, like 4 or 5 inches below, and then take a sample there, and you want to take several mixed samples from around the yard. Well, I already know my pH is off in varying sections of the yard, so I didn't want to go ahead and run multiple samples and wind up going down and paying $6 for each one of those samples. It takes an awful lot of time, so it's a whole lot easier to have your own meter. Now, with all the background information out of the way, let's talk hardware. I'm sure somebody's going to tell me, hey, what about these? They're dirt cheap. They're easy to use. Well, I agree. I actually bought one. Felt kind of dumb after I did it when I started finding out the main power source is one little small photocell. And of course, that alone should have told me the thing would vary all over the place. And it doesn't use the fundamental principles for measuring pH in the first place, as we're going to be getting into here in just a few moments. Well, at the heart of any pH meter is the actual probe. The little bottle I pulled out here is a little solution that is provided with the probe to keep the probe tip wet at all times. Never let a pH probe dry out. The probe I have here has a BNC connector. You can also buy them with SMA connectors. As you can see here, this probe has a little cap on the end of it. That holds the fluid and makes sure the probe stays wet at all times. This fluid is a special fluid, and you need to buy that. It's not tap water, so you definitely want to buy the proper fluid for storing your probe if you happen to run out of the fluid that comes with the probe. You can definitely buy pH meters with the probe built into the meter. I definitely would not recommend this, as you should consider the probe a part of an expendable, replaceable item. They will go bad. The lifetime of a probe is definitely dependent on multiple factors. Number one, how much it's used. Number two, what it's used in. And of course, number three, the quality of the probe to begin with. The particular probe I have here was bought off eBay. It sent me back a grand total of $11. A real good commercial probe is around $50. An industrial probe, glad you asked. They can run over $1,000. As you might imagine, something this cheap is going to have a few compromises, and it does, and we're going to get into all those as we discuss this a little further. Okay, let's get into a few more details. In my case, you have a plastic overbody, and the probe itself is made out of glass. The glass is a very special glass. It's electrically conductive. The bulb on the inside is hollow. There's a sensor wire that's on the inside of it, as well as a interior fluid. Nothing should touch the glass part of the probe except what is actually being measured by the probe. This particular probe is designed to be installed vertical down. As you can see, there is an air bubble inside the probe. I'm going to put several links in the description. One, of course, on pH probe maintenance, pH in general, and then the pH concept, exactly what it is. It goes into a whole lot more detail than I'm going to go into here. Here are the specifications and the model number of the particular probe that I'm using in this case. Again, bought from eBay and of Chinese origin. The net effect of the probe in this case is generating a very small output voltage on the order of around 60 millivolts per pH as far as what the slope is. And yes, that output voltage is definitely temperature dependent. As you can see here, the higher the temperature, the greater the voltage slope. On a good high quality pH probe, that output is linear with respect to pH. Here we come to the first problem with my inexpensive probe. It's not linear. Chances are this actually curves. It's not actually two broke lines at zero. Now, if I was controlling a process with this probe, I'd definitely be concerned. But in this case, all I'm trying to do is get a pretty good value of about what the soil pH is. So I'm not too concerned about the variation here. Now it's time to tell you the electronics that I put together to interface with this probe. In this case, it only consists of one operational amplifier, and I used a TL081 in my case. The TL081 is the updated version of the ever-faithful LM741. It also has the same advantage of being able to adjust the input offset voltage. It definitely needs to be a very high impedance amplifier because the signal is so weak. Recalling that positive voltage is acidic, I've elected to scale my operational amplifier output at 1 volt per pH, where in this case 6 pH is equal to 1 volt and 5 pH is equal to 2 volts, and so on. The test switch gives me the option of setting 0 for the op amp. As a practical matter, though, the 0 is set with the potentiometer as shown on the lower right, using a pH solution of 7. The scaling is done using the 10K pot up at the top and the 180K resistor. The 180K resistor will be the one variable item you'll have to determine experimentally depending on the probe you're using for your application. One of the main disadvantages of this approach is it does require split power supplies, plus and minus 5 volts. For those of you that would like to see what it looks like breadboarded, here's a quick view of that. Note that the potentiometers in this case are shown as single turns. Of course, I'm using multi-turn potentiometers in mine, as we'll see shortly. And here's my original prototype. I decided to leave it open on the top since I'm using my digital voltmeter as part of the meter. I connect up the output here and the ground for the meter here. This is my original prototype. I just wanted to cook up something pretty quick, so I go ahead and get some pH readings and get the soil compensated properly for this year's planting. I'm going to plant a couple gardens. I'm trying to get some grass to grow in some spots that's a little barren. The span potentiometer is on the right, and the zeroing potentiometer is on the left. The zeroing potentiometer is used at 7 pH. Here's my power connections and where the pH sensor connects up to. Well, now that I got this thing built, how do I calibrate it? Only one real way I'm aware of, and that's use buffer solutions. You can pick these up off of eBay for about 20 bucks. You get a 4, a 7, and a 10, and a probe storage solution. And knowing my propensity to knock things over, I decided to go ahead and put a little bit of the solution in 3 well-cleaned jam jars. These little miniature jars for jam samples, and I use these to actually dip the probe in. Since the jars are a little unstable, I go ahead and add a little adapter that you'll see shortly. And here's my entire setup, less the 2 other solution jars. I use a cut-off bottle top as a quick and easy fix to keep me from knocking the bottles over. And again, guys and gals, I'm still prototyping here. I'm sure there'll be some more refinements coming along later. Okay, step number 1 is to calibrate the 0 or 7 pH. And the probe is in a buffer solution of 7 right now. And I went ahead and turned the meter on, turned the power on. As you can see, the voltage is declining. It should be as close to 0 as possible. So I'm going to walk away for about 30 minutes and come back on this one. I've learned the probe isn't particularly stable, especially on 7 pH. So in this case, I'm going to say 0.07, 0.08 is close enough. I found out it does tend to oscillate a little bit on the bottom end like this. Okay, now that I've got my 7 pH 0 set, it's time to go ahead and change the solution. Obviously, I'm knocking off whatever's left of the 7 pH. I'll blow the sensor itself down to make sure I've got all the 7 out of it, and then lightly dab the outside with a paper towel. Next, I'll go to the 4 solution. Bear in mind here, of course, you'd probably want to actually go through this sequence twice if you're looking for a very accurate measurement. That means I'd go ahead and do the 4 solution after I do the 7. Then I'd come back and do the 7 again. Then I get it, make sure the 0 is correct for that one. Then I'd go ahead and go back and do the 4 pH solution again. That way I'd be sure my meter is as accurate as I possibly can make it. To speed the video up, I'm only going to do all this just once. I'll do the 7, then the 4, and then we'll do the test sample. What I'm doing here, of course, is putting a cover over top of the bottle. That way I can drop the probe in and I don't have to worry about knocking a little bottle over. The biggest problem with this method, of course, is cross-contamination. So you want to make absolutely certain that you've got all the pH solution you just measured with off with the probe, then shake the probe as best you can, then put it in the next solution, and then check and see what comes out. Well, you're probably wondering why, of course, the reading didn't go up. A very simple reason for that. I knocked the probe off when I moved the meter. So now I've hooked the probe back up. Now I get pretty close to what the proper reading should be, and obviously it's going to be increasing for a little while, so I'm going to go ahead and come back again in about 30 minutes. Now that's what I was looking to see, a reading of about 3 volts. It's going to bump around a little bit. I find out it's a little more stable on the top end than it is on the bottom end. Now it's time to go ahead and prepare the probe to actually test the sample. Again, same routine, get as much solution off as you can, then dab off the outside of the probe with a paper towel, making sure I don't contaminate my sample. I'm going to first take off my spill guard, of course, being sure I don't accidentally knock the bottle over. Then I'll put the cap back on the 4 pH buffer solution. Now it's time to go ahead and test my actual sample. What I've got is a clean as I possibly can get it glass jar. Glass is indeed the best material to use, and the fact that very, very little leaches out of glass into the liquid. The only other substance that's better for sampling liquids without contamination from the actual container itself would be tin. Since a tin container is kind of hard to come by, you're probably going to want to go ahead and definitely go with glass. I would not use plastic or any other metal for your container. You run the risk of the material itself in the container contaminating your sample. And by tin, I do mean the elemental tin, as in SN on the periodic table. In order to prepare the sample for testing, what I usually do is go out and get about a half a container full of soil. I've thoroughly checked the soil to remove any small rocks or roots, then add it to the bottle. After the bottle is filled about half full of soil, I'll go ahead and use rainwater or distilled water. Do not use tap water. Tap water has a pH of around 8, which is liable to artificially raise your pH level. I say that knowing, of course, most people looking at this are probably going to be in the southeast or the northeast. You California types out there with a lot of alkalis are just the opposite. What you want to do is to be able to use whatever liquid most matches your particular type of soil you're testing in. You don't want the water to artificially raise or lower your pH of your sample. The actual sample itself has been mixed about the consistency of a soup. It's more water than it probably is soil. I usually mix mine where it's even thinner than what you would usually call mud, unless you like a really, really light mud like you might find when you run a car through a mud puddle and you get a solid splash. The actual test procedure remains the same. Put the pH probe in the sample, then walk off for about 30 minutes. You want to make sure the voltmeter is definitely settled out and it's not jumping all over the place. If it starts to be a sinusoid, basically I take the average of the sinusoid and then pick that as the reading that I'm looking for. Now I'm sure somebody out there just said, hey dude, you just use a pH sensor that's not designed to measure soil pH. And that's absolutely true. You can buy sensors that are designed for this, that you basically can put in the soil directly. I found one pH sensor manufacturer on the internet that actually suggested a very similar method to this with a pH probe. And I found out it works pretty darn well. The only thing you have to make sure of is when you're finished, you have to take the pH sensor and thoroughly clean it with rainwater, making sure you get all the dirt off, and then put it immediately back into the storage solution. Well guys and gals, that pretty well wraps this one up. Hope you found it interesting and useful. It's probably beyond the ability of your average backyard gardener, but you guys out there know your way around electronics will have no trouble putting one of these together. You can probably pick most of the stuff you're going to need off of your electronic junk box. Personally, I find this approach to be a major time saver. I don't have to worry about maybe once a year taking the sample down, just check all the other elements in the soil. I could take pH readings and have an actual reading of the area I'm testing within about 5 minutes after I've taken the actual sample. In the case of this particular test, you can see the reading is moving closer back to 0, meaning it's 7 pH. So this soil is basically neutral. Well, thanks for watching. Hope you found it both interesting and useful. I definitely got a few more little tricks up my sleeve I'll be putting on the video pretty soon. So take care. Y'all have a great day and week. And this here's Engineer on the Side. We catch you on the next video. We say bye.